Good morning or afternoon, everybody. Thanks for the invitation. I'm happy to present the Post-AGB stars as tracer of stellar evolution. I'm in a different time zone. I'm also upside down, so I hope it will work out. I will focus this talk on the nucleosynthesis, and the reason for that is depicted in that graph. Is three spectral regions of three different stars with the same similar temperature, similar metallicity, similar luminosity. But you see that thanks to the post-AGB character, we are the stars are dominated by atomic transitions, and you see clearly the barium enhancement in the two upper stars. So I'll give a general introduction of post-AGB stars first. I'll focus a little bit on nucleosynthesis tracers, and then I'll come to the results on post-AGB stars. It will be quite confusing in a way because there is a much larger diversity than what you expected from first principles. Just to set the stage, this is of course very clear. It's an HR diagram. What we're talking about is post-AGB, so the stars left the AGB. It's a fast evolutionary track, and the position on which the post-AGB star is on that track is only dependent on, well, the luminosity is dependent on the core mass, or the white dwarf. There is a tiny layer of an envelope, and that envelope is a few hundred solar masses when you start the post-AGB track, and depending on how that envelope is diluted, you increase the effective temperature. So there is a direct link between the effective temperature of a star and the amount of mass in the envelope. And you have to remember that because at the end of my talk, I will turn back to that. So the post-AGB star, so in the literature, there's many names for post-AGB stars. So astronomers are very bad in giving names. So you have protoplanetary nebula or pre-planetary nebula sometimes, but these are linked to the envelope. And today I will focus on their central star, so really the photosphere of the central star, and I call them post-AGB stars. It's a fast evolution. Let's say from 1,000 to 100,000 years, the star changes dramatically from one solar one solar radius to about one radius of a white dwarf. You go from 3,000 Kelvin to 100,000 Kelvin. And in that track from the AGB to the PNE phase, you also pass instability strips. So many of them are variable, and we call them population 2 Cepheids, but almost all objects are variable at some stage. They change from very obscure to naked, in which the line of sight to where the photosphere is about the envelope is not opaque anymore, and you see the photosphere. So I will focus this talk on objects for which we see the photosphere. They're very diverse, so we are prone to a very large variety of observational biases. For one post-AGB star, there are about 1,000 AGB stars. The only problem is that we don't know which ones, because there is quite some uncertainty on how to link a certain post-AGB star to the AGB population that precedes them. I will focus on the nucleosynthesis, and so this is a graph that you're probably all familiar with. I just want to focus on a few things. So this is the intershell, the time versus mass coordinate. Time is not linear because the intershell phase is about 10,000 years, sorry, and the pulse itself takes about 10 years or so. Whenever there is a pulse, the hydrogen burning shell is switched off, and after the pulse, there is a phase in which you can dredge up material, so you bring enriched material to the surface, but also you penetrate protons into the intershell. If that protons is, if you penetrate many protons, you will make nitrogen 14, which means that you don't make the S process, so you don't make carbon-13 pocket. So you really have the right amount of protons. You need the right amount of protons into the intershell to create the carbon-13 pocket. The carbon-13 pocket is the onset of the CNO burning, but it stops at carbon-13. And that will burn via the alpha N reaction to oxygen-16, and this is one of the neutron sources. The neutron sources is in a radiative environment. You have the whole intershell period to create your Hess process nucleosynthesis. If you integrate over the 10,000 years, you get an integrated neutron flux of about 0.3 millibarn. The densities associated with this Hess process is about 10 to the 8 neutrons per cubic centimeter. The next thermal pulse, you will mix that all material. You will mix the material which is enriched in those Hess process elements over the intershell. If the temperature is hot enough, you can burn neon 22 alpha N, and you make another burst of neutrons, making which is higher in density, but lower in time, smaller in time. So there is a different nucleosynthetic origin of the carbon-13 pocket and a neon-22 neutron source. Then again, depending on how much envelope mass there is still in the envelope, you will dredge it up and you will have a lambda parameter, which is a dilution parameter. The S process stands for slow neutron process, as you know. The R process, which is the rapid neutron process that related to nucleosynthesis in a environment which is explosive, is much higher neutron densities of 10 to the 20 per cubic centimeter, which gives rise to a very different nucleosynthetic process. So just this is a recapitulation. So the S process follows the path of stability. That means if you capture a neutron, you capture a neutron, you capture another neutron until you hit a unstable nucleus that will decay. And so you climb up the value of stability along the value of stability, in fact. So you climb up the neutron charge along the value of stability. Useful to know is this is the equation governing the nucleosynthesis. So the change in an abundance of a certain element depends on how much is created by the previous neutron capture and how much is removed by neutron capture on the element itself. This tends to go to zero, so it's an equilibrium. That means that the abundance times the cross-section is a constant. So if you have a low cross-section, you have a high abundance. If you have a high cross-section, you have a low abundance. And if you look at the cross-sections, you see there are very deep valleys in the magic numbers, 50, 82, because at those cross-sections, these are very low cross-sections because the neutron shell is filled. You have the same with the protons. And if they combine, you have double magic, it's called, and that's typically lead. Lead is in fact the end product of our nucleosynthesis because it's double magic. You have Z. So the protons are magic, the neutrons are magic, and you have a very, very low cross-section. That means lead will pile up as soon as you reach lead. So what you will observe of those S-process nucleosynthesis is really dependent on how much neutrons you have captured. This is depicted here. It's a bit a complicated picture, but I'll run through it. So this is the atomic mass. This is the abundance. And dependent on how much neutrons you have captured, you will increase the abundance of heavy elements. So how do we observe it? Is by observing. So how do we differentiate the different neutron irradiations? Is by observing many lines, many elements all over the mass range A. And that's where the post-AGB stars are useful because the spectrum is dominated by atomic lines. So you trace a wide range of elements via your spectral analysis. We typically differentiate between LS and HS. So LS is a light S-process elements, which are typically strontium, yttrium, zirconium because of the magic number 50. HS is the heavy element, is barium and lanthanum, so is around the magic number 82, and the lead peak is double magic. Yes. There is now a new kid on the block, which is the I process, and the I process is a neutron irradiation with densities intermediate between S and R. It was introduced already a long time ago in 1977, but it's now quite, it's getting more and more attention. The reason is that in the SAMP stars, so the carbon enhanced metal poor stars, some of them have both an S process nucleosynthesis pollution as well as an R process nucleosynthesis pollution. And it's difficult to imagine that in two different processes, that you have pollution by a supernova and pollution by an AGB star. And so there are ways to look for regions in nuclear space, let's say, where you have create densities which are in between. So that's why the I process gained a lot of attention. The recent years, so this is depicted in the right figure, in which I just used ADS to search for the name I process in the abstract, I think. And so you see in the last years, there's a number of papers increased dramatically with respect to the I process. There's a lot of debate on where this I process is occurring. It can be in low metallicity AGB stars, and I'll come back to that. So where do you receive, where you can create this high neutron densities? That is, if you introduce protons into the intershell, but into the shell itself, so during the thermal pulse. This is normally, in a normal evolution, is not the case, but at low metallicity, it may be, and I go back to the slide, sorry, if you connect the shell, so the pulse, in fact, with the protons coming from the envelope. So if you connect those two, and that it may happen only in low mass, low metallicity AGB stars. Other regions are not so relevant for us today, but there are many sites in which the I process may occur. The pointers to the I process is really the profile of heavy element abundances. And this is another picture which may be a bit complicated. This is europium versus iron. This is lanthanum versus iron. And so we have the S. So this is all SEMP stars, so carbon enhanced metal poor stars. The R process is here. So it is really, it's high in europium and low in lanthanum. And there is an intermediate region where the RS stars are found. So it's really depending on the distribution of heavy elements where the tracer of the I process is located. Oh, sorry, that's your way around. So why are post-AGB stars now interesting? This is because they are dominated by atomic transitions. So as far as once you see the central star, you can take a spectrum of the photosphere. It's dominated by atomic transitions, in which it's much more easy to find a wide range of elemental abundances, because you're not veiled by the molecular bands. The lower one is a carbon star, and you see it's much more difficult to trace the very small abundances of heavy elements. Another reason to go to post-AGB stars is that we are lucky enough to have a significant number of them. In the galaxy, it has been thanks to the infrared surveys. In I think the Magellanic Clouds came thanks to Spitzer. Spitzer gave a very good photometric, in the infrared, a very good photometric coverage of stars with infrared excesses. You can use this to trace the rare post-AGB stars. And so we have a good sample. Still, it's a very low in number. You see there are about 209 likely galactic post-AGB stars. I close the window because there's some noise. And we have similar numbers in the LMC and SMC, so we can really do some statistical studies now thanks to that number. But still, it's low in number. You will never have a huge population of post-AGB stars. And that's one of the problems to interpret the results in a global astrophysical context. Oops. Post-AGB stars are multi-wavelength objects, because you have the infrared, of course, where the dust is shining, and you have the photosphere. We focus in this talk about the stars where we have the photospheric, where we can trace the photospheric abundances. This is another example of 3 spectra. So this is a very tiny region, and all the S process elements are marked either the zirconium, so the light S process elements or the heavy S process elements. You can trace up to Wolfram and in fact up to lead. So you have and we do it in this LMC as well. So you see here, that was the picture I started with a clear abundance of overabundance of barium in this case. The post-carbon stars, so the elements for which C over O is larger than 1, you see most of them are very S process enriched. You see you go up to 100 times the solar value, and that gives a very, although the elements by number is still very low, of course, the abundances themselves in absolute number is not very high. Your spectrum is often dominated by those process lines because they have a very rich spectrum. My favorite in the SMC is G004441. This object, if you look at the spectrum, is really completely dominated by S process lines. All the lines you see almost is S process. The top one is a galactic object with similar metallicity, similar temperature, similar gravity, but the spectrum is completely different and completely dominated by those S process lines. It's a 21 micron source, which is a dust feature which is not identified yet, but is associated with the carbon-rich nature of the central star. You have pHs, so you can combine whatever you know from the infrared also to the photosphere. This is one of the most S-process rich objects we know. So it's up to 1,000 times the value of the sun. It's quite rich in, and so the added value of focusing on Post-AGB star is really that you have a whole range of elements that you can trace via your atomic transitions. If you fit then the abundance distribution with models, it is doable. So you have a rather good fit depending a bit on the dilution factor. There is one big caveat, is that if you go to lead, we do not see the overabundance of lead. And that is one of the problems or one of the challenges, is that in most post-AGB stars, we do not trace lead to the value that should be there because of the nucleosynthesis. So this is the light S process peak, this is the heavy S process peak, but you see the green one is the model that fits best and fits quite well. You see a huge difference between what is predicted by the models and what is determined by the spectra. This is the spectral region. Lead is a bit of a difficult element because it's only a few lines. It's only a few lines in the blue. The spectrum is black. The model is the best fitting model is green in this case. And this pink line is the spectrum that you would expect if the lead was as abundant as the models predict. We did then a more systematic study, and this is also, again, a complicated figure. This is iron, this is lead over HS, and we only see upper limits. And so this is the line which is predicted by the models. In fact, at low metallicity, you see that our upper abundance are in fact lower than the value of the model. So we really have a lead problem at the lower end of the metallicity range. For the solar, so more solar metallicities, there is not much constraint because our upper limits are much higher than what the models predict. Another interesting challenge is that because the neutron source is primary, it's building up carbon-12, which is made by the star itself, there is no strong link between the initial metallicity and the neutron production. That means at low metallicity, per iron seed, you have much more neutrons than at high metallicity. So you would expect to have a high, efficient nucleosynthesis if the metallicity is low. But this is not really, within the metallicity range that we probe, this is not really observed because it's really a cloud of objects, and I would not dare to call this any correlation. So this is another challenge, is that the diversity of neutron irradiations is much larger than what the models predict, and certainly with respect to metallicity. The chemical diversity goes the other way in the sense that there are also objects in which we do not probe the S process overabundance, despite the fact that they are very similar in luminosity, they are very similar in metallicity. So this is an example, two objects with very similar metallicity, very similar luminosity as well. But you see this one is not at all enhanced and this one is very enhanced. So the fact that some objects do produce the third redshift with S-process overabundance and the others don't is something this still of a concern or a challenge. This is another example. This is now a peculiar star in the SMC, so we know quite well the luminosity. It's a low metallicity, minus 1.2. The luminosity is 9,000 solar luminosities. If you look at the spectrum, the green one is the star. The lower one is a galactic object with S-process overabundances. You see there is no way you can this is an observational mistake because we derive abundances, of course, but the spectrum is completely devoid of S-process lines. Similar objects exist in the galaxy. So if you add everything together, we have quite a few objects in which we think they are not affected by another mechanism, but they avoided the third redshift. So that comes to an overview. This is now a slightly strange plot because this is metallicity on the y-axis. Metal poor stars are on the top, metal rich stars on the bottom, and this is S-process overabundances, in which this is S-process rich and this is S-process poor. I don't know why we plotted it that way, but anyway. So the red one is the S-process overabundant objects. The blue ones are the S-process there's non-enriched objects. You see there is a gap, of course, between, but there is no link with metallicity whatsoever, which is a bit contradicting to the stellar evolution theory. If you put those stars into the HR diagram, you have to say that the luminosity is still quite uncertain because the distances are such that the error on the luminosity because of the parallax error is quite large, but still you do not see a very clear image that the, let's say, more luminous objects are more enriched. In fact, it's a mixture of very much the same population. So this adds to the chemical diversity. Another system which adds to the chemical diversity is what Maxim told you about this morning, is the depletion. So depletion is a chemical process in which the objects lose their nucleosynthetic history, but they are coated with a layer of gas which comes from the circumbinary disk. It affects very strongly the chemical composition, so the spectrum, and this is a dramatic example in which the top one is a comparison star, which is a normal Post-AGB star with the same metallicity, not the same metallicity, but the same temperature, the same gravity, and you see the effect on that depletion is severe. This is another example, is just to show that the effect can be very strong. Zinc is not affected, and this is the key, that was the key to understand the system. So I can go quickly over it because Maxim told you about this. This is a depletion of elements depending on the condensation temperature. It's a process which is a circumstellar process, so it's a chemical process that occurs in the surroundings because the star accretes material from the surrounding, and that material is devoid of refractories because dust formation has occurred in that material. We did proceed with understanding the system quite well in the last decade, let's say, because all those objects turned out to be binaries with a certain environment in which there is a circumbinary disk. So we understand now, well, understanding is a large word, but we can point to the physical mechanism responsible for that depletion pattern is that the objects are in binaries. There is a circumbinary disk. That disk, from that disk, there is an accretion of material. That accretion is coming from the disk, but the dust is trapped in the disk and the gas is floating to the central star. It seems to be a very strange scenario, which is fine-tuned a lot with respect to what is needed. So you need a binary, you need a circumbinary disk, you need an accretion, but in fact, it's remarkably common that we see those abundance patterns. It's only linked to binaries. We know because we follow them for a long time with our spectrograph at La Palma. And we have next talk will be on Casper on those binaries specifically and on the orbits we find, because the orbits are a bit strange with respect to what we would expect. Back to the depletion. How do we know that? So how can we model that? If the material which is accreted gives you a certain abundance pattern, so this is condensation temperature versus the abundances. This is a material that on which that is accreted onto the central star. With a factor of 2 dilution, you don't see a lot of effect. With a factor of 100 dilution, you see the effect strongly. And if you're saturated, then the material that you see on the photosphere of your star is completely dominated by the accreted material. So there is no link anymore to what the abundances was in the first place. You can model that. You can see how can we understand it, and that was done by a PhD student here, Glenn Michael, who modeled the accretion using a MESA model of a star which was devoid of the envelope, and to see how can he link the position of the HR diagram now to the accreted material and to the abundances by the star. The amount of material that you need to accrete is quite significant, and for some objects that does mean a quite prolongation of the evolutionary time, because you accrete much material and hence you prolong the post-AGB lifetime. Here you see that this figure is zinc over titanium, iron over titanium, and so the red and the green and the whatever color that you call is all depleted objects. So you see it's really common observed. So we do see in post-AGB binaries, the depletion scenario is very common. More common than you would expect, because those objects all turned out to have a disk, and the disk seems to be very efficient in creating that complicated process in which you accrete the void material. It does complicate life because the synthetic history, so the nucleosynthetic history of the object is then completely vanished, and we don't trace eventually dredge up stars anymore. Magna has found one object or discussed one object or a few objects where that AS process is still available. So to conclude, the chemical or the photosphere of post-AGB stars are intriguing or rich. We find the most S-process rich objects that we know, but on the same hand, we also find non-enriched objects. And the distinction between the two is not very easy. It's not with respect to metallicity, so there must be more parameters that determines whether a star will go through the third dredge-up or not. And on top of that, the chemical diversity is larger because of that depletion, which turns out to be very commonly observed, and certainly in binaries. So to conclude, some post-AGB stars are the most S-process rich objects we know, so that's cool. Galactic LMC and SMC objects have now significant samples, so we still need to study it more systematically, but we are getting there. There is no clear metallicity dependence on the HS over LS ratio, which is a bit contradicting to what we expect from purely nucleosynthetic reasons. Even at low metallicity, the S-process rich objects do not produce lead, so we have to find, and the I process may be important there because the I process can produce high S-process elements, but not lead, but it's still very much work in progress. Many post-AGB stars are not enriched at all, so we have to find mechanisms that are common and that are blocking the S process to occur. We do not differentiate the haves and the have-nots, and depletion is a chemical process which is now understood in the sense that we know the conditions under which it occurs, but that does not mean that we understand the full process. So there are still many puzzles to solve, and systematic studies are still needed. I started with saying that the connection from the post-AGB stars to the AGB stars is not completely clear. I think for some object it is, so the post-carbon stars are quite well connected to carbon stars, but there is still a lot of debate in which objects on the post-AGB sample represents which stage of AGB stars. And with this, I think my time is finished, and I wish you a nice trip tomorrow and enjoy the wallabies.
Thank you. You mentioned that you connect the depletion to the binaries. So
Yes.
what do you see any kind of depletion also in single post-AGB stars? Let's say those that are these shell type post-AGB stars?
No.
So those all of them show like S processes that.
Yeah. So either they are S process enriched, and then the S process is they are refractory. So the S process will not be seen when there is a depletion ongoing. But in none of the non-enriched objects, so there are a sample of objects which are not enriched, but also not depleted.
Okay.
And all the depleted objects that we know are either in proven binaries or have a disk in which we suspect that the disk is related to binarity.
Okay, thanks. Yeah.
It's possible you mentioned this, but I missed it. Exactly how much, at least order of magnitude, how much mass do you need to accrete in order to achieve the necessary depletions?
So it's about 10 to the minus 7 or 10 to the minus 6, depending a bit which object.
Great, thank you.
And that is when you follow, so what Glenn Michael did is he used a MESA model, he let it evolve, then removed the envelope at the end of the AGB, and then started to accrete, let the star evolve, and find the star in the right spot in the HR diagram with the correct abundances. And by playing with the mass accretion rate, it ends up to be 10 to the minus 7, about 10 to the minus 7 per year.
10 to the minus 7 solar masses per year. That's the
Yes.
accretion rate. The total mass, what was it? Because I can imagine here that the important thing is the total mass, isn't it?
No, I think the most important one is the accretion rate, because you lose mass because of the luminosity as well, and because of the consumption because the star still consumes the envelope because of the nucleosynthesis. And so you lose about 10 to the minus 7 because of nucleosynthesis. So you accrete 10 to the minus 7, and then you end up in a steady state.
Okay, I see.
What dust properties are needed so that the dust avoids getting accreted with the gas? That's a good question. I don't think it's a dust property, but it's more like the disk property. And so within young stellar objects, you also see depletion. But in young stellar objects, you have the model is that you have a dust sink. So your dust is trapped, in fact, in the disk by a planet. And so the planet provides a pressure bump. The pressure bump sticks the dust particles in that location, and the gas can flow through. In post-AGB stars, this is an intriguing possibility, but of course, we don't know whether there are planets in the first place or whether they are newly created planets. So this is another ongoing research to see what kind of structure that we can find in the disk that can provide the pressure bump which is needed for the dust to be trapped. But the fact that it's so common means that it's really a mainstream process.
Hello, Hans. It's Jolien.
Yes. Hello, Jolien.
It's a bit of general questions about post-AGBs, but do you know from all the observations you have, how many, like what percentage of the post-AGB stars are clearly in binaries and how many are just single stars, or is that difficult to tell from observations?
So the total, so if you look at the numbers, bare numbers, the best way to do that is in the LMC and SMC, because there we have a better complete sample, let's say. It's about 30% which have disks.
Yeah, okay. And those that don't have disks, that then
we assume that they are, well, we don't know, but we assume that the companion if there is a companion, is wide enough such that the dust is not trapped in a disk. So it doesn't mean that they are single. It only means that the companion is far out so that there is no circumbinary disk.
Okay, I see. Thank you.
Because the circumbinary disks within our sample that we know the orbits from, the orbits are limited to, let's say, the period is about, the largest period we have is 2000 days. So it's a few AU, so 5 AU or so, but not further.